Hello there, and thank you for joining us for the third in the OpenLearn podcast series. Now, we've got something very exciting today. Today, we are going to be looking up as well as forwards, and you will find out more why in due course. But we are talking to Dr. Jo Barstow, who is an Ernest Rutherford Fellow here at the Open University, and we're going to be talking exoplanets. So that's the reason for looking up, and welcome, Jo.
Hi, Ben. Thanks very much for having me.
That's an absolute pleasure. Now, I've had the absolute joy of talking to you before about exoplanets, so you were someone I definitely wanted to invite here to have a further conversation. So I want to start off with and just sort of say exoplanets. I mean, planets, I think a lot of people are familiar with. Exoplanets, maybe not so. So exoplanets, what are we talking about?
All we're talking about is planets that happen to orbit a star that isn't the sun. So all the stars that you see when you look up in the night sky, probably most of them, although you don't realize it, actually have one or more planets in orbit around them. And that's what I spend my days studying. I try and find out more about those planets in other star systems.
Okay, I mean, you said that's what you spend your days doing. So let's go down that route a little bit. A research fellow at the Open University. What do you spend your days doing? What are you working on? What is your work?
Well, I'm an atmospheric physicist and a planetary scientist. So what I do is use light that's come from usually space telescopes like Hubble and JWST, light that has been captured by those telescopes, coming from those distant star systems that has passed through the atmosphere, the sort of outer shell of gas surrounding some of these planets. And that light contains sort of fingerprints of what the composition of that atmospheric gas is. And that can actually tell us an awful lot, not just about what the atmosphere is made of, but about how it might have evolved, how it's behaving, how it's moving around, how it responds to different conditions. So actually, these objects, they're kind of our laboratory for understanding how planets and their atmospheres work as a whole.
Wow. Okay. So there's a few people out there I think are probably already kind of googling how to become an atmospheric physicist, perhaps, and what's needed. That sounds a pretty cool thing to be doing with your day. So, I mean, what does that actually involve? What are you using? How do you measure this light?
So, as I said, usually we use space telescopes. This can be done using telescopes on the ground as well. But the trouble with that is that our atmosphere has a bit of a tendency to get in the way. So, space-based observations are immune to that, and that makes it somewhat easier. And mostly at the moment, I'm using data from the relatively recent space telescope, the James Webb Space Telescope, that was launched quite memorably actually on Christmas Day in 2021. And the reason that that telescope is so impressive and useful for this particular type of science is that it's an infrared telescope. So it's not sensitive to the kind of light that our eyes can see. It's sensitive to infrared radiation. So that's the radiation that those little forehead temperature sensors we all got so used to during COVID, that's the kind of radiation that they are sensitive to as well. But JWST is sensitive to a vast range of different colors, if you like, of that radiation. And that is really, really handy for detecting things in planetary atmospheres like, for example, water vapor, which you probably agree is a pretty important chemical. It's certainly very important for life on Earth. Actually, it's pretty much everywhere. We've seen it in nearly every exoplanet that we've studied, but also other chemicals like methane that you might be familiar with, carbon dioxide. So I'm looking at light that has passed through the atmosphere, being collected by that telescope. Fortunately for me, that somebody else has usually cleaned up and made into a fairly nice, neat sort of wavy line with little bumps and wiggles in it. And each of those little bumps and wiggles corresponds to the fingerprint of one of these gases. And what I actually do day to day is mostly get very annoyed with computers because I use computers at the Open University, but also some of our national high performance computers to run simulations of light passing through an atmosphere and then compare those with what we've actually observed from the telescope.
So on the telescope, you mentioned a couple of names, the James Webb and Hubble. I think they're probably sort of names that people would recognise. Just tell us a little bit more about those telescopes. I mean, how powerful are they? And you say that's what you're looking at to detect the gases and so on. I mean, are these telescopes used to find out more about exoplanets that we already have discovered, or is that how we're actually finding them in the first place as well?
Oh, this is very much looking at planets that we've already discovered. These are not really detection engines, although that's not to say they couldn't serendipitously, by chance detect a planet, but they're not detection engines. These are looking at planets that we already know about. And certainly in the work I do, the subset of planets that I'm looking at are ones that have been detected using a particular method, and that's what we call the transit method. And that's basically where a planet passes in front of its star from our perspective. And when that happens, it blocks a little bit of the starlight. So if you're monitoring the star and you're measuring the amount of light coming from the star, then you can see a dip. And if you see the dip happen again and again and again, it's always got the same depth. That tells you that there's a planet orbiting the star. And the kinds of telescopes that make those measurements are sometimes in space, sometimes on the ground. There have been two really key space missions so far, Kepler and TESS. There is another one that we'll be launching in the next few years called Plato. That's a European Space Agency mission that aims to look for planets that take longer to go around the star than most of the ones we've found out about already, because it's much easier to do this for planets that only take a few days to go around their star because they come back around nice and quickly. They're also more likely to transit. Plato's actually going to be looking for planets a little bit more like the Earth potentially, so periods of several months to potentially several years. And also there's several ground-based telescopes that do that detection as well. But what I do is very much following up on those detections and looking for more details.
Can you give us any kind of sort of comparison? Even the good telescopes that we might have, the people who can can go out to the bottom of their garden and a big chunky telescope that not like the old ones that I used to. I remember I had a £10 telescope in my Christmas stockings that you could barely see to the end of the road with. How do these super telescopes compare with the best things that us as amateurs can get our hands on? How much more can we actually see?
Well, I guess ultimately it comes down to mirror size, right? The bigger the mirror, the more light you're collecting, the more sensitive you are. So JWST has a mirror that's about 25 square meters in area. I think, and that's pretty big. That's certainly bigger than the telescope that you might have stuck in your garden shed, or hopefully not stuck in your garden shed, hopefully being used on a regular basis. And it's bigger than quite a lot of telescopes on the ground, but actually we're now starting to get into the era with ground-based telescopes of the extremely large class of telescope, which will be actually more sensitive in terms of mirror size, at least, than JWST, but with that handicap that I mentioned earlier, that they are on the ground, therefore they can't see stuff that doesn't make it through our atmosphere, which is quite a lot of stuff in the infrared. That's why it's so important JWST is in space. So it comes down to collecting area. It also comes down to things like the precision of the alignment of the mirror. So you may have seen pictures of JWST, and if you've seen a picture, you'll know that it's not a round mirror, it's hexagonal, and it's not a single mirror either. It's made up of hexagonal segments that tessellate with each other. And something that had to be done after launch while it was in space, but before it started taking science data, was to actually make sure that those mirrors were all absolutely perfectly aligned. So each of those mirrors has a little actuator on the back that allows it to be tilted and moved to make the alignment absolutely spot on. It has to be very, very good to get the quality of image that you want from a telescope like that. So to give you an idea of the kind of signals it can detect, if you've got a planet that's the size of Jupiter, orbiting a star the size of the sun, it blocks out about 1% of the total light coming from the star. So not a lot, but also, I mean, that's actually a reasonable amount. So for a Jupiter transiting a sun, just to detect it, just to say yes, it's there, you can do that with a fairly small telescope. And in fact, students at the OU regularly use our own telescopes that are on Tenerife, which are not particularly big, to measure transits of planets. So this is something you can do with a relatively small telescope. But if you're doing what I'm doing and you're looking for the atmospheric signatures, what you're interested in measuring is not the overall depth of that transit. It's the variation in the depth of that transit in all of those different colors of light. And that's about another factor 100 at least smaller. So that's now about 1 part in 10,000. And that's for an easy planet. For a difficult planet, so when we're starting to get down to things that are smaller than Jupiter, we're not even quite at Earth yet. Earth is still really difficult. Earth around a sun is very hard, even for JWST. But for, say, something a bit smaller than Neptune, you're talking maybe 10 parts in a million, a few tens of parts in a million. So it's a tiny, tiny signal that we're interested in measuring. And that's something that you simply can't do with a smaller telescope. So Hubble, which is obviously a space telescope, but it's been doing absolutely exquisite science for more than 30 years now, it couldn't make some of the measurements we can now make with JWST. It's mainly partly because the mirror is too small, partly also because it's in a much sort of less stable area of space. It's orbiting the Earth once every 90 minutes, whereas JWST is at a little sort of sweet spot in the Sun-Earth system where it's permanently shaded by the Earth from the sun, and that makes it much more stable. So JWST is really at the very limit of what we can do right now, and it's been an absolute game changer.
Now, the reason I said at the start about sort of looking up and looking forwards was because, well, just to let everyone else in on this, just before we started, Joe messaged and said, oh, if it's of interest, I was in the US last week and we were talking at a conference, I believe, about sort of NASA's next new telescope or observatory. So that's why I've gone down this route of telescopes and wanting to know where we are now and what's coming next. So perfect opportunity. Brag to us about your time spent in the US talking NASA and observatories and the future of exoplanet exploration, I guess.
Oh yeah, I mean, so I had a very, very intense but an absolutely brilliant week last week in Washington DC, and the reason I was there was that there was a conference that was being held to bring together scientists and engineers to talk about the next great observatory that NASA wants to launch. So we're talking, this is going to be in about 20 years' time. So if any of you are listening to this podcast now and you're sort of in your late teens and maybe thinking about your career, listen up if you're interested. This could be the thing that you're working on in 20 years' time. It's very much looking at the future. And this is called the Habitable Worlds Observatory. So the aim of this next great observatory is to put a telescope in space that's not got a much bigger mirror than JWST, little bit bigger, but the real advantage of this telescope is it's going to be able to take a picture of an Earth-like planet around a sun-like star in our relatively near neighborhood around our sun. Not just one, of course, several. So this is hopefully going to be the telescope that tells us if there is another Earth out there, if there is another rocky planet out there that has an atmosphere that's anything like ours. And when I say take a picture, I don't actually just mean take a picture, although it will do that. It will also be able to give us information about the atmosphere of a planet like this. So it will tell us, does its atmosphere contain oxygen, ozone, methane? It could also tell us potentially, is there liquid water on the surface of this planet? Because liquid water has a very specific reflection signature. And this will be a little bit like Hubble on steroids, actually. So it's not an infrared telescope. It's an optical telescope with a little bit of ultraviolet sensitivity and a little bit of infrared sensitivity. So it's going to be a general purpose telescope. Lots of astronomers doing lots of different exciting science are going to be using it, but its main sort of goal, its raison d'etre, is to do this. It's to find another Earth and potentially find indirect evidence of life outside of the solar system, which I think would be absolutely transformational science on so many levels.
Oh yeah, I mean that's one of the questions that everyone is always most interested in, isn't it? Is like, is there life out there? Is there another planet like Earth? So let me ask you, have we come close, not close to thinking we found another Earth, but have we found other planets out there? Have we found anything that has given us that the idea that yes, it will exist, we will find it? Anything that sort of even resembles Earth?
So we found evidence of Earth-sized planets around a number of different types of star. So we know that Earths are out there. That's not in question. Pinning down the exact sort of frequency, the number of them, the reason that's so difficult at the moment is that all of the methods we've got for detecting them, most of them are very heavily biased towards planets that are bigger, heavier, and close to their stars. So I mentioned the transit method already. It's biased towards larger planets because they have deeper transits, but also just because of geometry, the further away a planet is from a star, the less likely it is to be lined up just right to transit. That's just a fact. And other methods that we use, some involve measuring effectively how much the star is wobbling due to the gravitational interaction with the planet. That's also very much biased towards closer planets, heavier planets. So it's not that they're not out there, they're just very difficult to detect with the methods we currently have. And that's partly why Plato, the mission that I mentioned earlier, that's going to potentially be able to detect longer period transits, that's why that is so important. And also the other way we can hopefully detect these is to use some of these extremely large ground-based telescopes that are coming up over the next few years, which will be more sensitive both to measuring wobbling stars, so it might start to push down to Earth mass things, but also will have at least maybe some capability to, if not to characterize, to maybe directly detect something small as well, maybe. So the way that when I talk about direct detection, the big problem that we have is that, well, as everyone knows, right, stars are much, much brighter than planets. It's just a fact, it's a given. And we're trying to spot something next to something that is very, very, very much brighter than it, a long, long, long way away, and they're very, very close together from our perspective. It's really, really difficult to do, which is why most of our detection methods so far they're indirect, if you like. They're measuring the influence of the planet on the star rather than looking at the planet directly. And the way that we kind of have to do this is effectively, I mean, if you've ever, I don't know, if you've ever played tennis or something in bright sunlight when the sun's starting to set, and you're trying to see the ball, you put your hand up to shade your eyes because you're trying to block the sunlight. So that's basically what Habitable Worlds Observatory and what some instruments on ground-based telescopes will do. They have something in them, and it's called a coronagraph. It was designed originally to be able to see the outer layers of the sun's atmosphere, which is called the corona, by blocking out the light from the brightest bit of the sun. It's exactly what happens actually during a solar eclipse, where the moon provides that blocking facility and you can see the solar corona. And so basically it's a stop, it's a block in the optics of the telescope that allows you to get rid of the light from the star and only see the things around it. It's of course far more complicated than that. It's not as simple as just having one block, because when you put anything with a sharp edge in telescoped optics, things diffract, they scatter off the edge, you get all sorts of mess, if you like, little speckly patterns on your detector that you don't want, so you have to get rid of those. It's a very, very complicated piece of engineering. But Habitable Worlds Observatory will have a coronagraph that will enable it to detect something that's not 1 part in a million, not even 1 part in a billion, 100 parts in whatever 1,000 billion is, which I can't remember. That's the kind of contrast we're talking about between the Earth and the Sun, and it will be able to detect that. So phenomenally tiny little signals.
That's incredible numbers. I mean, I think we all know that it's it must be it take incredible technology, incredible power to detect these things. But that's just unbelievably. I can't think of the right word to describe it. It's beyond something that you can kind of even picture or work out, isn't it? It's that's unbelievable. When we spoke before, there's a couple of things I remember you telling me. So some sort of bit more simple answers now, perhaps than coronagraphs and 100 parts in 100 billions and so on. You told me that there was around about, I think when we last spoke, around about 6,000 exoplanets that had been discovered. Um, is that where we are? How often are exoplanets actually being found? If when we last spoke it was around 6,000, is this an everyday occurrence? Are they popping up all over the place?
I mean, it's still around 6,000. It tends to go in waves. So when there's a brand new mission, like something like Kepler, for example, that's optimized for doing this, you get a sudden sort of gush, if you like, of detections. Because each new mission is designed to look at, I guess, a different bit of discovery space. So we had a gush with Kepler, we had a gush with TESS, and both of Kepler is now finished and TESS is still going, but it's found most of the low-hanging fruit now that's easy for it. So that gush has sort of slowed to a trickle, but there is still a trickle. There are still planets being discovered all the time. And ground-based telescopes that are looking at wobbling stars, they're also discovering planets all the time. So it's at the moment we're in a steady trickle phase. With something like Plato coming along in the next few years, I imagine there'll be another gush. So I don't know. I forget exactly what the yield is supposed to be from Plato, but it's a lot. We're talking, hundreds, thousand. And there's also the Gaia spacecraft that has now finished its mission, but the data is still being sort of looked at. And what Gaia did was measure the positions of stars on the sky incredibly precisely. And so once that has all been sort of processed and analysed, by monitoring little positional changes on the sky of some of these stars, that will also lead to planet detections as well. So we're exploiting every possible method. There's also a telescope launching from NASA in the next couple of years called the Nancy Grace Roman Space Telescope. That is also going to find planets using the same methodology as Habitable Worlds, but also by looking at what we call gravitational lenses. So if you've got anything that has mass, it will be bending light very, very, very slightly. You probably won't notice it most of the time. But if you've got a star and a planet and something much brighter behind them that passes behind them, then they can act as a lens. So you see this little temporary brightening of your distant star. And if you've got a star and a planet, you get 2 bumps instead of 1. That's a really powerful detection method for planets, and Nancy Grace Roman will be doing that as well. So all the time we are finding new planets, but it very much is it's waves, right? There's a mission, you get loads, then it slows down.
Before we finish, I mean, I just want to ask you what it is that perhaps that you're most excited about coming forward. I can sense your excitement, your enthusiasm as you talk about this subject, which is fantastic. But yeah, what's the most exciting thing for you that's coming up?
Oh, I mean, obviously, particularly after last week, I'm so excited about Habitable Worlds because it's getting down to looking at not just other planets, which are all fascinating, but solar systems. Because it's not just Earths we'll be able to see. It's Jupiters, Saturns, Venuses. One of the things I've always wanted to learn, because I started out my career actually studying Venus as a solar system planetary scientist, is how many Venuses are out there relative to Earth? How many are, the Earth gone wrong scenario with Venus that lost its liquid water really early on, got too hot, now is an absolute hellhole with sulfuric acid clouds, and how many of them actually stayed a reasonable place to live? I really want to know. And we have absolutely no idea actually about the split there at the moment, and maybe eventually we'll be able to learn that, and that would be really, really exciting. But in the nearer term, the telescope I just mentioned, the Nancy Grace Roman Space Telescope, it's a little bit like a sort of pathfinder for habitable worlds. So it's not going to be as sensitive. It's not going to be detecting any Earths, but it might be able to give us a first look at some planets that are like true exo-Jupiters. So we've seen loads of Jupiter-sized things that are much closer to their stars, so they're really hot, or things that are Jupiter-sized and hot because they're young. What we haven't really seen yet are things that are actually like Jupiter in our own solar system, that are cold gas giants. And I'm really hoping that Nancy Grace Roman Space Telescope, it might actually start to give us the first little bit of information about one of these cold Jupiters, and that would be really cool.
Fantastic. Well, then let's hope that that comes to fruition. Let's hope you get to find out what it is that you want to know, if there's any more out there. And yeah, that's been absolutely fantastic. Thank you so much for joining us today, Jo. And that's been brilliant. And just want to finish by saying, if you want to know more about Jo's work, there is a free course on exoplanets on OpenLearn. So please do go and check that out. Like the videos, give us a subscribe, click on that bell to make sure you don't miss any new ones coming up. And yeah, thank you very much today for joining us today, Jo. It's been absolutely brilliant. Really appreciate your time. Thank you.
Great. Thanks. Bye.
And we'll join us again soon on the OpenLearn podcast. Thanks very much. Bye-bye.
If you enjoyed this clip, feel free to follow the links on screen for more interesting articles and free courses from the Open University.